This is the complete presentation of the KDD2021 paper, Initialization Methods, Regularizing Manifold-informed Initialization for Neural Recommendation Systems. I'm Yinan Zhang from Nanyang Technological University, Singapore. This is joint work with Boyang Li, Yong Liu, Hao Wang, and Chunyan Miao. Recommendation systems have been playing an increasingly significant role in our daily life, which recommend an item to a user based on the user's interaction history and profile. Deep neural networks have been widely applied in recommendation systems. However, a recent finding indicates that the simplistic k-nearest neighbor method can outperform many sophisticated neural networks, casting doubt on the effectiveness of deep learning for recommendation. And the power of KNN lies in its use of the neighborhood structures on the data manifold. As neural networks tend to converge close to their initialization, a natural thought is to initialize neural recommendation networks with the neighborhood information. Since Laplacian eigenmaps is a well-known technique for creating low-dimensional embeddings that capture multi-scale neighborhood structures on graphs, one possible idea is to apply LE into KNN graphs in recommendation. Given an undirected graph G with n nodes and non-negative edge weights, we use W to denote the adjacent matrix, where Wij refers to the edge weights between node I and node J. We use D to denote its diagonal degree matrix. The degree Di is defined as the sum of edge weights of node I. Here is an example on the right. The edge weight of the first node D1 is W12 plus W13, which is 2. Then we have the unnormalized graph Laplacian L, defined as D minus W. Alternatively, we use the normalized symmetric graph Laplacian in our work. To find node embeddings, we compute the eigendecomposition of the graph Laplacian L, where the column of matrix Q are the eigenvectors from Q1 to Qn, and matrix lambda has the eigenvalues from lambda 1 to lambda n on the diagonal. Then, we select the eigenvectors corresponding to the smallest d eigenvalues as the matrix Q tilde. The rows of Q tilde become the embeddings of the graph nodes. We show the first 4 embedding dimensions sequentially as bars overlaid on every node. Positive values are in red and the negative ones in blue, and the bar lengths indicate the absolute values. Each dimension of LE embeddings divides the graph into clusters. We observe only one cluster in the first dimension, 2 clusters in the second dimension, 3 in the third one, and 4 clusters in the fourth dimension of the LE embeddings. In summary, later dimensions of LE embeddings feature greater fluctuation between the neighboring nodes. In other words, the LE embeddings divide the graph into clusters of increasingly finer granularity. However, direct application of LE ignores an important characteristic of the KNN graph, that the graph edges are estimated from different amount of data and hence have unequal variance. For users and items with short interaction history, one more additional interaction record leads to large changes in their LE embeddings. This is undesirable because our dataset contains only partial observation of reality. We don't want to be overly sensitive to missing records. We perform a simulation by adding random edges to nodes in random graphs. We record the original degrees of nodes and the changes in the LE embeddings after adding the edge. The results are shown in this diagram. Graph nodes with fewer adjacent edges experience more drastic changes in their LE embeddings. This indicates that the LE embeddings for relatively isolated nodes are unreliable because a single missing edge can cause large changes. To address the problem, we propose Laplacian eigenmaps with a popularity-based regularization for isolated data, or LAPRID. The method regularizes the embeddings for users and items with short interaction histories, serving as variance reduction for the estimated embeddings. For Laplacian eigenmaps, it can be understood as solving a sequence of minimization problems. The eigenvectors from Q1 to Qd are solutions of the constraint minimization. Then, keeping the constraints unchanged, we add a regularization term to the minimization function in LE, where Dmax is the maximum degree and alpha is the regularization coefficient. The added term applies stronger regularization to the nodes with smaller degrees. In the matrix form of LAPRID, we define the graph Laplacian with popularity-based regularization, LREG. We can solve the sequential optimization using the same eigendecomposition procedure on LREG. However, eigendecomposition that solves for LE and LAPRID embeddings has a high time complexity of O(n) cubed for a graph with n nodes, which does not scale well to large datasets. Fortunately, for the k-nearest neighbor graph, the graph Laplacian is a very sparse matrix. Utilizing this property, we can compute the first d eigenvectors with the time complexity of OK² d kappa, where kappa is the conditional number of L. Note that this complexity is independent of the graph node number n. In our experiment, it only took about 3 minutes to compute the 64 eigenvectors for the user Knn graph on the anime dataset. In comparison, it took about half an hour for the simple BPR embeddings, which are commonly used in initialization, to converge. We have shown you how to find the embeddings when the graph is given. Now we show you how to generate the Knn graph. We construct two separate similarity graphs, respectively for users and items. We define the similarity between two users as the Jacob index. To maximize the benefits of the proposed initialization schemes, we designed the network dual loss residual recommendation DLR². We use user embedding and the latest interaction history to represent users' current preference. We regard the next item to interact as the target item and randomly select an item that have not been interacted as the negative one. We have three networks. We use the feature network to generate users' current state, SIT. Then, we feed it into both the discriminative network and the generative network, which exploit complementary aspects of the supervision. In the feature network, we employ residual connections, which may create invertible outputs and preserve all the information in the input embeddings. We hypothesize that this may allow the network to fully utilize the power of initialization. Given the user and item, The discriminative network evaluates how much the user prefers the item, while the generative network directly predicts the next item that the user will interact with. The final loss is the sum of discriminative loss and generative loss. The discriminative loss forces the target item score to be small and the negative item score larger than the threshold MS. The goal of generative loss is to make the distance between the user and the target item small and the distance between the user and the negative item large. We evaluate the proposed initialization schemes and the recommendation model on 3 real-world datasets: movie lens, Steam, and anime. We use hit ratio and F1 score to evaluate the top-end recommendation. We select a comprehensive list of initialization methods, including graph embedding methods, pre-trained graph transformer embeddings, random initialization, SVD, and pre-trained embeddings from BPR. We then apply different initialization into deep recommendation models, including NCF, NGCF, DGCF, and HGN. We also compare against traditional recommendation methods, including top pop, which always recommend the most popular items, traditional KNN approaches, including user KNN and item KNN, and matrix factorization approaches, including BPR and SLIM. We summarized the comparison of different initialization in the General Collaborative Filtering Method, NCF. The best initialization results of each model are in bold faces. The second best results are underlined. The relative imp refers to the relative improvement of Laprid over the best baseline other than LE, which is marked with a star. We observe that the choice of initialization has strong effects on the final performance. For example, on movie lens, the F1 score of Laprid are over 10 times of random initialization. Besides, Laprid consistently achieves the top position on most datasets and metrics. LE is a strong second. We have the same observation on the performances of sequential recommendation method, HGN, and our proposed sequential model, DLR². The initialization is important, and our proposed initialization, Laprid and LE, achieve the best and the second best results. On 2 different recommendation methods that use graph convolution, we observe the same effects that Laprid and LE perform the best and second best. Importantly, we also observe that even though the 2 methods are based on GNN that already utilize graph information, they benefit substantially from Laprid. This suggests that Laprid is complementary to common graph networks. We also compare traditional recommendation methods, Laprid initialized recommendation methods, and the DLR² method with LE and the Laprid initialization. Relative imp indicates the relative improvement of DLR² with Laprid initialization over the best baseline within the group. Similar to the earlier results from the literature, we find well-tuned user KNN and item KNN competitive. Among traditional recommendation methods, the 2 KNN methods claim the top spots on all metrics of all datasets. However, on movie lens and Steam, Laprid initialized neural recommendation baselines perform on par or better than the KNN methods. This finding highlights the importance of initialization for recommendation systems. Importantly, DLR² with Laprid initialization outperforms all other methods, including strong traditional models and the well-initialized neural recommendation models. Laprid adaptively regularizes the embeddings of nodes with low degrees, which should benefit users with short interaction histories. In this experiment, we verified that claim by examining model performance on the 25% of users with the least interaction records. From these results, we observed that Laprid achieves higher relative performance improvements on tail users than on the entire test sets. The simple model of DLR² has achieved the best performance thus far. We also explored the architectural factors that contribute to its success. The literature suggests that residual connections are invertible and may improve the quality of learned representation, which may facilitate DLR² in fully utilizing the strength of the initialization schemes. In order to investigate the effects of invertible representations in DLR², we create a RevNet variation for the network, which guarantees to produce invertible features. Compare the RevNet variation and the original ResNet architecture in DLR². We note that RevNet achieves comparable performance, which suggests that learning invertible representations may facilitate the effective use of good initializations. In conclusion, to capture neighborhood structures on the data manifold, we propose to initialize user and item representations with Laplacian eigenmaps. To the best of our knowledge, this is the first work applying LE in initializing neural recommendation systems. Further, we identified the issue of high variance in LE embeddings for Knn graphs, and propose Laprid to reduce variance for users and items on the tail of the data distribution. We also propose a new network architecture, DLR², to effectively utilize the superior initialization. On 3 real-world datasets, DLR² initialized by Laprid surpasses all baselines, including traditional and proper initialized deep neural networks by large margins. The source codes are available in GitHub. If you have any questions, please send us emails. Thank you.